37 degrees. This will be somewhere around 30. And, no, wait, cosine of 37. So this will be somewhere around 40, this will be somewhere around 30. I think we're about to get more detailed.
39.9 and then 30.1.
All right. Obviously, that's a bigger number. So that's associated with this right here. This is 39.9 newtons, and this one would represent 30.1 newtons. Now, that might have been completely independent of what the question you asked was. However, do you have a follow-up, or did that clear it up, or?
It did. I didn't think we had to put in the numbers. I thought we were supposed to. So, yeah, now I get it.
It's the panic situation. You know, you can put numbers in any place that you want. It's just, I tend not to till the end. And hopefully why will become a little bit clearer before we're done today. Abigail, did you have your hand up?
I did not know.
Okay, Riley?
Quick question. Does newtons have like another form that makes the units make sense when you multiply them?
A newton is what is known as a derived unit. It is by definition. So equal by definition, equal to a kilogram times meter per second squared. That is a newton.
Oh, okay.
So. Or?
Is this what is weight equals mass times gravity, acceleration due to gravity, sorry. Is that what we would consider the equations of motion, like one of them, or is that
No,
something different?
no, that kicks in usually during the substitution phase.
Okay,
It is an independent formula. W equals mg is not problem specific.
okay.
Robin, you okay? That,
Yeah.
would I overreacted?
Yeah.
Okay. It was not directed at you, it was directed at the hundreds of students I've had in the past do the double. But they're not here.
So basically, I'm their like successor or something.
Was that?
I succeeded their like mistakes, like it manifested in me or something.
It's entirely possible that will be your best student.
I've just heard it enough. I'm trying to think of how do you actually convince students that kilograms is not a unit of force or a weight. And especially when in biology, I believe, more specifically, it is used, or if you watch British television, they talk about weight in kilograms. I mean, how do you actually convince people that's not the case? Because, you know, I'm fighting programming of anywhere from 16 to 60 years.
Yeah, a pretty good way would be traveling back in time and convincing you not to take chemistry right before this.
Yeah, that's so true.
I was blaming biology people, but you blame chemists now?
You have a lot of ops, is all.
Okay.
I learned kilograms is weight because of Miss Williford.
Yeah.
Yeah.
Yeah. Just got done saying it.
Oh, I'll give her a piece of my mind. Oh, she probably already heard it because no doubt she's watching these videos.
Oh. Hi.
She's got better to do.
This should be illegal.
All right. I actually, I have talked to her before about that, and I'll talk to her again. And I'll name your names, and you will blaming you specifically.
Fooey.
Where were we? Ah, we had just finished up the decomposition phase.
Yep.
Equations of motion.
Wait. For decomposition, which one did we choose?
We
Cosine
decomposed
sine.
the weight.
So what's our equation for a vector?
Oh.
Wait, sorry, what?
Don't we have to make an equation to make the weight to a vector? So like, hold on.
We have a direction right there, so we've already indicated the vector piece.
So which of the values would be j hat and which one of the numbers will be I hat?
Well, we defined I hat down the ramp, J hat perpendicular to the ramp. So these would be the I hat ones, those would be the J hat ones.
Oh, okay.
All right, equations of motion, what's the template for linear motion for equations of motion?
F equals MA?
That's the one.
Yeah.
Newton's second law. So we have one object with two dimensions, two directions, so we'll have two equations. We'll have an I hat equation and a J hat equation. It'd be convenient is if you're gonna label them like I just did with I hat and J hat, so just keeping track. It'd be helpful if you don't put an equal sign after the I hat and the J hat. So my I hat equation, we just look at the force diagram. If that's done properly, we're good to go. We just look at that and go, all right, what's going in the positive? We're doing the forces. What are the positive I hat forces?
So
Friction.
positive, it's the one from the way.
Okay, positive I hat is down the ramp.
It's, it's
So,
the
friction
third.
motion,
So
right?
W sine theta. All right, any others in the positive I hat direction?
No,
Minus, what's in the negative I hat direction?
friction.
There we go. Is equal to,
Mass times rate of acceleration.
because we've established acceleration is gonna be down the ramp. So with a magnitude of A, boom. I don't need a subscript next to the mass because I have only one mass. J hat,
The normal force minus W cosine theta. Equals MA.
Which is,
Mass acceleration. What? Wait, what am I?
what is the acceleration in
Oh,
the J hat
zero.
direction?
Zero.
If this were also MA1, you have the same, it's accelerating, I guess you'd have the two components the same, and so it'd be accelerating at a 45-degree angle from the ramp. But the whole point of picking our coordinate system is so that one of these equations is equal to 0.
So when we're doing, equations of motion, well, for right now specifically, we were just talking about the box, like.
Yes.
Okay. The ramp comes up at some point, or?
No, we did the forces on the ramp just for completeness, but we really only care about the box. The box is what's gonna accelerate. We assume that the ground is so massive, the planet is so massive, it is not going to move appreciably because the box is sliding down the ramp.
Alright.
It is close enough to at rest.
We're finding out the stuff with the box, and that was the question.
Yes.
Okay.
Ultimately, what's the acceleration of the box?
Yep, yep.
Which I thought intensely, but I don't know if I stated explicitly.
Who knows?
And as you stated earlier, your mind reading skills just don't turn on.
It's like this land around.
All right, so now, substitution. Sorry, after the equations of motion, what's next?
Substitution.
Do we have an independent formula for anything on here?
Could you divide by, like, I don't know if this is what you're asking, but if it's like running into an equation, could you divide the I hat by A? So that you can just combine the two equations by M?
You're going into the solving solution part already.
Oh,
Substitution,
Weight can be substituted for mass times gravity. Gravitational
it's just,
force,
weight is a gravitational force.
M times G.
Yeah, there we go, just mg, just save the hassle. So yes, we have a formula for weight, so this becomes mg sine theta minus the friction is equal to ma, and then we have normal force minus mg cosine theta equals 0. There is an independent formula for friction, we're not worried about that right now. We will get to it.
so the M's are the mass of the box,
Yes,
even the MA.
That M is also of the box.
So we divide M on each side?
All right, so let's get into solving. So the first scenario, so if we were dealing with, if I started out with no friction, then the only difference is the F part disappears. If there is friction, we're gonna end up here. It's just as easy to assume that there's friction and then take the friction out than to try to put friction back in later. So we're gonna, so case one, frictionless. And I missed what you said, Naomi.
Oh no, I'm thinking to myself.
Okay, so case one, friction is equal to 0.
Wait, so for the J hat, did we remove the mass because the acceleration is 0?
Anything times 0 is 0, so I just went ahead and
Alright.
did that multiplication.
So we are getting rid of friction or we're not getting rid of friction?
For the first scenario, we're getting rid of friction.
Okay, so it'll be mg sine theta plus y minus mg cosine theta equals ma plus 0?
That would be a true statement, but unnecessary. If we're solving for acceleration, I have an equation here. I know m, I know g, I know theta. So I know this, that. I have, at this point, I have 3 unknowns, a, f, and y. Right here, I'm establishing f, so now I have 2 unknowns. One's acceleration, one is the normal force. I could calculate, if I'm trying to find the acceleration, there's no need to bring this equation into it.
Okay.
In the frictionless case, this equation is just sort of sitting there. It's the appendix of the problem. Body part appendix, not the book appendix. So if we divide by mass, so that this equation now becomes mg sine theta equals ma. We can divide by m, and so a is equal to g sine theta. And so my acceleration of the box will be 10 times the sine of 37 degrees. Which is about 6.
Oh, sorry.
No, this one's like 6.05.
So we just remove m because we divided it out?
Yes,
Okay.
So we're just back to.
the mass is irrelevant,
Oh, okay.
as long as it's not 0.
So,
Take
About
6.01815.
815.
Yeah.
meters per second squared.
Questions here? Because we're about to bring friction into it. Touch reality. Go on.
So to save ourselves confusion, maybe we don't, I know we did it as like an example, but maybe we don't we don't already go ahead and solve for weight yet.
Right, I mean, one of the advantages of plugging numbers in at the end is the mass canceled out and we saved ourselves a math step.
Okay,
Some students like to plug numbers in as quickly as possible because that works for them.
okay,
There's nothing inherently wrong with it. Potentially, you're gonna add more work to yourself later, but if it's clearer in your head, it's worth it. If you pursue physics long enough, and I suspect most subjects, you'll get to a certain point where you don't use numbers anymore anyway, it's all letters. Until you get into an experiment. Okay, let's talk about friction. First off, let's just accept that if I take this notebook and I slide it across the table, based on Newton's second law, if acceleration is 0, the total force has to be 0. If acceleration is 0, the velocity is constant. So if the net force is 0 on this, and I gave it a push, well, actually, whether I push it or not, if the net force on it is 0, then the velocity should be constant. Same speed, same direction. So if I push on this and it stops, the velocity changed, therefore there was acceleration, therefore there was force. There had to be a net force acting on it, or a net non-zero force. The thing that's stopping it, assuming you're not subscribing to the demon theory, is this thing we call friction. The question is, what affects the amount of friction between the table and the notebook?
The amount of surface area that is touching the other surface.
All right. There could be friction even in it when you're far from any gravitational field. So first off, let's talk about weight. Then we'll hit surface area. Anyone else? So we have surface area, weight.
I was gonna say the distance travels.
The distance
I
traveled.
mean, that kind of relates to the surface area.
Okay. Oh, the distance of contact?
Yeah.
Ah, okay. All right, so first, weight. So as crudely as I can, trying to figure out some way of coming up with an even push. So keep my arm stiff, just twist the fingers, okay. Roughly the same slide each time. I'm now going to put this on here. And let's just put all this stuff on here. Is it going to slide as far if I apply the same amount of force?
No.
It didn't. Does the notebook weigh any more than it did before?
No.
No, wait, notebook.
Friction is between the table and what?
No.
The notebook. Did the weight of the notebook change?
No.
So weight is not the issue. What did change when I piled all this stuff on here? What changed between the notebook and the table?
The amount of
True force got
the gravitation,
Wait, what did you say?
the normal force.
Yeah, it's the normal force.
I'm a normal force.
Okay.
Normal.
There are a number of people who love to call it the natural force. I think I heard neutral, but you might say natural. It is normal. The normal force changed. Think of normal force as if I have two surfaces touching each other, then normal force is the indication of how tightly they're pressed into each other. So the greater the normal force, the more they're pushed into each other, and if there are any idiosyncrasies in the surface, if there are any nooks and crannies that you get, think of puzzle pieces, they get shoved in more. So you increase the friction if you increase the normal force. Surface area. And we have friction blocks in the other room. Let's see how well I can balance this. Not well on that. Let's see what this will do. All right, so now I'm going to use the surface between this and that. It slides a certain distance there. It's not going to stick particularly well. All right, and if I put it like that, what are the chances it will fall off? Very poor. All right, so let's think about it conceptually, since no, that's not going to work well. If I spread that force out over a larger surface, then if I look at any particular point on the notebook, there's not as much pressure. The pressure drops because it's spread out over a larger area, things sitting on a bed of nails. If I sit on a single nail, that's probably going to penetrate. So if I have a smaller surface area, all that weight's concentrated into a smaller surface. So there's gonna be greater force per square inch, but there's less of it. And it turns out that it actually balances out. So, yeah, nice if I had a really good demonstration here. I'm sorry, I don't. Surface area does not seem to have an effect, unless the surface has different textures on it. Which leads to the other factor. Besides the normal force,
They're having a birthday party for a dog from my school.
Congrats.
Is that what the,
Yeah.
that's out of,
I'm sorry. I just had to explain it because they're happening.
oh, is that the music?
Yeah.
Okay.
As soon as I get out of here, they're done.
I thought you just wanted me to know.
Flashing back to lawyer versus physicist. All right,
Sorry.
at least there's some context here. So besides the normal force, what is the other factor that affects the amount of friction?
Material.
Yeah, materials, both of them. If you look up a table of coefficients of friction, you will find they'll give you a list of two things. They won't give you one and another and you somehow combine them. It's a combination of the materials. So mathematically, we have normal force, so friction depends upon normal force, and it depends upon the coefficient of friction, which is dependent on the two surfaces involved. We have a mu sub s, a mu sub k, and potentially just a mu. Now, why are there just a mu or a mu sub s, mu sub k? Depends upon the textbook. The formula for friction was developed in I believe the late 1700s. At that point, they had something that's workable. So physicists tend not to work with friction. In my particular case, I was dealing with subatomic particles breaking up and smashing into each other. There's really not friction at that level. The other group that would deal with friction are engineers, and they have something that works, and engineers, as a general rule, are very practical. So I know there was a group at NC State, I assume they're still working on it, and have been trying to come up with something more sophisticated than the 300-plus-year-old formula.